This is chapter 4, number 44, the one with the 2 blocks. One's trying to slide down. You may want to reread this question before watching this video. Make sure you're familiar with what's in there. I'm going to go ahead and start by drawing a picture and a free body diagram for both blocks. So here's the big block, which I'm going to label block 1, and the small block, which I'm going to label block 2. Here's a frictionless surface. So there's no friction here, but there is friction as this block 2 is trying to slide down. So my free body diagram for block 1 will be the normal force up, or the ground on the block up, and that's the normal force of block 1. The weight of block 1 down, or label that as earth on block 1 going down. And then we have force P, which I think they called, or no, force F, sorry, different problem. They just called this F. So this is F acting on the block to the right. And you might think that is all the forces, and we'll come back and add a force to this one in just a minute after we do the free body diagram for block 2. For block 2, it's trying to slide down because of the weight. So we got the weight of block 2 down. And what's keeping it from sliding down? Friction. Since it's not moving, that's force of friction static. And since we're trying to limit this force F, let me just make sure they called that F. They did not. They did call it P. Force P for pull, probably. We're trying to limit this force P. We're trying to make this small. We want our static friction to be big as it can get. We're trying to get P to be as small as possible and still have this work. So I will put force of friction static max. We're talking about the maximum value of static friction right before, or we're trying to use as much static friction as we can to keep the thing from sliding down. There's another force here. Block 2 is in contact with block 1. Because we're pulling block 1 to the right, it's sticking to block 1. So block 1 is going to push on block 2 to the right. So I'm going to write this 2 ways. Force of 1 on block 2. And all these other ones were on block 2 as well. Friction on block 2, earth on block 2. So force of 1 on 2, which is also known as the normal force. And that is the normal force of block 2. I'm going to use that variable when I sum forces, but that's the same thing as 1 on 2. Now the part that many of you may have missed the first time you tried this problem for the free body diagram for block 1. If we have the force of 1 on 2, Newton's third law tells us there has to be the force of 2 on 1. Or the idea of if you push on the wall pushes back on you. Those forces go in separate free body diagrams. They have equal magnitudes and opposite directions. So what does that mean? 1 on 2, there's a 2 on 1 going the other way over here. So force of 2 on 1, which I can again represent with the variable Fn2 if I'm referring to the magnitude. At some point I'll have to account for the fact that this is going left when I sum my forces, but there's the magnitude. If you didn't get the free body diagrams right, you cannot get this problem correct. You shouldn't have been able to luck into it. You got to have these right and then keep your work organized, which is why I've given myself a little more room. I'll be a little bit neater on this one. I'm going to sum forces now like crazy, and hopefully, and use the equation for friction, and hopefully we'll end up with an answer for, I think we're trying to find what P equals. Doesn't matter where we start, so let me just write down a relevant equation over here, that force of friction static max equals mu sub s times the normal, and for this problem, the block that's got the friction is block 2, so we're using this Fn2. In the original problem, I think they gave us, we've got the mass of the blocks, and we have the coefficient. So mu sub s is something that we know. So that's good. We haven't even gotten P into an equation yet. So if we're trying to solve for force P, I better sum the forces in that direction. So I'm going to sum the forces in the x direction for block 1. So that'll equal the mass of block 1. And since these 2 blocks are stuck together, it's similar to me running with a desk. These are big desks. If I run with this desk across the room, the acceleration of me and the desk are the same because we're stuck together. That's true up here as well. Since these 2 objects are moving off together, their accelerations are the same. So it's sufficient to just call this A, because it will be the same variable over here as it is for block 1. So how many forces are there in the x? There's 2. So force P minus, and I'm going to call it Fn2. I've already done the thinking about the fact that these have the same magnitude, and there's where I'm accounting for the sign. So minus that Fn2, that's the variable I'm using, equals M1A1, or M1A, sorry, it's sufficient to say A. So we know the mass of 1, and we don't know anything else. So this looks bad again, we're stuck, but at least we introduced another equation that had what we're looking for in it and shares a variable with over here. So I'm going to keep summing forces. And I know I need to do something with this normal force too, because it's in both my equations. So where else does that pop up? Pops up for block 2. So summation of forces in the x direction for block 2 equals mass of block 2 times A. Only one force, Fn2 equals M2A. And we know M2. So we've got to get another equation with Fn2 in it. But I still think we're stuck because we don't know Fn2, we don't know P, we don't know static, and we don't know A. So we have too many variables for the equations we got up here, so I'm going to keep summing forces. I'm going to go ahead and sum the forces. Static friction's in here, so let's sum the forces in the y direction on block 2. So summation of forces, I'll do that up here. Summation of forces in the y direction on block 2 equals M2A. There are 2 forces in the y direction on block 2. So force of friction static max. Oh, what I'm calling up and right positive. It's never not on my paper, you can assume that. Force of friction static max minus weight 2 equals M2A, and now we're getting somewhere. We can get weight 2 because we know the mass, and it looks like I think I have enough equations now to solve. Let me box some stuff off and then see.